Hello everyone, I am Akshay and my PLN is 19 series 51. So my presentation topic is CD nozzle. So the flow of the presentation will be like CD nozzle, then the area Mach relation and assumptions, then pressure distribution for different back pressure, then exit velocity, exit Mach number, over expanded and under expanded nozzle, and then I will show CI4. So CD nozzle. So first, what is a nozzle? Nozzle is a passage used to transform pressure energy into kinetic energy. Basically, it increases the velocity of the fluid and decreases the pressure of the fluid. As we know from the Bernoulli's law, we can derive that equation that pressure is inversely proportional to the velocity. So first pressure is higher and velocity is low. So through the nozzle we increase our velocity and then thereby decrease pressure. So a CD nozzle is used to generate the supersonic flow and is sometimes called as D-level nozzle on the name of the scientist. And it is widely used in some type of steam turbines and is an essential part of the modern rocket engine and the supersonic jet engine. So this converging and diverging portion helps to achieve the supersonic speeds. So this is the area Mach relation which relates the Mach number, velocity and area for the CD nozzle. So when the flow is subsonic and area is increasing, then it causes the velocity to decrease. And for supersonic flow, if area is increasing, then the velocity will increase. So in the converging section here in CD nozzle, if flow is subsonic, then and area is decreasing, so the velocity will increase, and at the throat it will be equal to Mach number equal to 1. And then in supersonic region, the flow will further increase its velocity as Mach number increases and the velocity also increases and pressure decreases in the diverging section. As from our area Mach relation, we can say that. So assumptions for CD nozzle. For simplicity, the combustion gas is assumed to be an ideal gas. The gas flow is isentropic, that is at constant entropy, and it is frictionless and adiabatic, that is there is little or no heat gained or lost. The gas flow is constant, that is steady during the period of the propellant burn. The gas flow is along a straight line from gas inlet to exhaust gas exit, and that is along the nozzle exit symmetry. Nozzle axis of symmetry. The gas flow behavior is compressible since the flow is at very high velocities. So now we'll see the pressure distribution for different values of back pressure. So consider the flow in convergent divergent nozzle as shown in figure. The upstream stagnation conditions, that is initial conditions at the inlet, that are the pressure are constant, and the pressure at the exit of the nozzle is denoted by PE, and then the pressure nozzle discharge to the back pressure, that is PB. With the valve initially closed, there is no flow through the nozzle and the pressure is constant at P0, and opening the valve slightly produces a pressure distribution as shown in curve 1 here, and it's completely subsonic flow. It is the never reach Mach 1. It diverges again to the subsonic after increasing some Mach number, then again it decreases. And then PB is lowered in such a way that sonic condition is reached at the throat as in case 2. So here Mach number reaches 1, but it further not increases and again come to the subsonic flow, and the flow rate becomes maximum for given nozzle and the stagnation conditions. So on further reduction of the back pressure, the flow upstream of the throat does not respond. However, it back pressure is reduced further. In cases 3 and 4, the flow initially becomes supersonic in the diverging section, but then adjusts to the back pressure by means of normal shock standing inside the nozzle. In such cases, the position of the shock moves downstream as the PB is increased, and the curve 4, the normal shock and stands right at the exit plane. Flow in the entire divergent portion up to the exit plane is now supersonic. When the back pressure is reduced even further, there is no normal shock anywhere within the nozzle, and jet pressure adjusts to the PB by means of oblique shock waves outside the exit plane. A convergent divergent nozzle is generally intended to produce supersonic flow near the exit plane. So for supersonic flow, CD nozzle is must. Like for subsonic flow converging section, that increases the Mach number up to 1, and then to carry forward from that, if we don't attach the divergent section, the flow will again come to the subsonic region after reaching Mach 1 due to shock waves or some other reasons. So divergent section is attached to the convergent section, and then if the back pressure is set at 6, the flow will be isentropic throughout the nozzle and supersonic at the nozzle exit. Nozzle operating at PB corresponding to curve 6 in figure are said to be at design conditions. Rocket propelled vehicles use convergent divergent nozzles to accelerate the exhaust gases to the maximum possible velocity to produce high thrust. So again we see that the figure. So first two curves are subsonic exit velocities, which has Mach number less than 1, and flow is isentropic. First curve never reaches the Mach 1, but the second curve reaches the Mach 1 and then again comes back to the subsonic region. Then third curve is acoustic velocity in throat followed by shock waves in the divergent flow, and the flow is non-isentropic. Then the fourth curve, supersonic flow in divergent with jet separation and oblique shock waves. And then fifth, the oblique shock in the exit section with no jet separation. And last one, Mach greater than 1, expansion waves at the nozzle exit. So exit velocity, the speed of the compressible fluid UV at the exit plane called the isentropic discharge speed, is given by these equations. UV equal to into root 2 into h naught minus he. So this will be derived in this way, and we can get the exit velocities. So then exit Mach number, this is the equation for exit Mach number. So exit Mach number, this is the relation for exit Mach number. Then for isentropic flow of perfect dash, these are the isentropic equations. Then with this we will put in the exit Mach number equation. Then we will get final expression like this. Then these are the over expanded and under expanded nozzles with the different Mach number and pressure back pressure conditions. These are the uh, shock interactions that will occur after the nozzle exit for the different back pressure, ambient pressure conditions. So for the CI4, I have made the nozzle with the help of paper, and also done the CFD in ANSYS Fluent. Then I also tried the flow or a supersonic airfoil, that is diamond airfoil. I have not got the complete good picture, but it's uh, it's giving a little idea about that. Thank you.